Now, our next discussion is regarding the maximum height and the time of flight depending on the vertical component of the initial velocity. We know that the vertical component of the initial velocity is u cos theta. So at the highest point, y is equal to h, vy is equal to 0 because velocity at the highest point is 0. Therefore, h is equal to uy square over 2g. This is in accordance with the equations of the uniformly accelerated motion, and because vy square is equal to uy square minus 2gy, this is also in accordance with the uniformly accelerated motion. Or maximum height will be h is equal to u square sine square theta over 2g. We can also determine the horizontal range, that is r. So in order to find the range, we consider x, horizontal distance. So x is equal to uxt, where ux means the horizontal component of the initial velocity along x-axis. R will be ux into capital T. Now we have computed the values. So R can be written as u cos theta into 2u sin theta over g, and this is estimated as R is equal to u square sin 2 theta. So from where we got sin 2 theta? Sin 2 theta means 2 sin theta cos theta. So that is sin 2 theta. So range is calculated by function u square sin 2 theta divided by g. Now we have taken the vector form. So velocity at time t is vt, and vt is equal to vxt I plus vyt j, where I and j are the unit vectors along x-axis and y-axis. Then vxt is replaced by u cos theta, and vy is replaced by u sin theta. So we have written that vt will be equal to u cos theta I plus u sin theta minus gt j. Again, I am repeating that I and j are the unit vectors along x-axis and the y-axis. Now from this, by using the equations for vector, velocity is calculated, that is u square cos square theta plus u sin theta minus gt the whole square. Now, there is certain note here which is very important, the alternative equations of trajectory. So whatever calculations we have done earlier, they can be further written in a different way. That is, equation of trajectory y can be taken as x tan theta into 1 minus x over r, where r can be taken as 2u square sin theta cos theta divided by j. If we wanted to further evaluate it, 2 sin theta cos theta can be written as sin 2 theta trigonometrically. Now, the vertical component of the velocity is Vy, which is 0 when particle is at the highest point of the trajectory, because velocity at the highest point is 0. When we throw a body, gradually its velocity goes on decreasing, and at the highest point, the velocity becomes 0. So we have taken vertical component of the velocity Vy as 0 when the particle is at the highest point of trajectory. Now in the third point, you can remember that vertical component of velocity is positive when particle is moving up. Vertical component of velocity is negative when the particle is coming down, and the resultant velocity of the particle is calculated by the rectangular components of the velocities. So V is equal to under the root Vx square plus Vy square. Vx means velocity along x-axis and Vy means velocity along y-axis. And the angle of projection was phi, so it is found to be tangent inverse Vy over Vx. Basically, the equation was tan phi is equal to Vy over Vx, and we have to calculate phi. So we have taken the inverse function. That becomes tangent inverse Vy over Vx. Displacement from origin is given as x square plus y square under root. Now, if the angle of projection is changed from theta to theta dash, say 90 minus theta. Now here, if trigonometrically we have to go, sine 90 minus theta can be taken as cos theta and cos 90 minus theta can be taken as sine theta. Therefore, the range r dash for angle theta dash is given as u square sine 2 theta dash divided by g, or this can be written as u square sine 2 into 90 minus theta over g. Now sine 2 theta can be written as, that is, sine 90 minus theta is cos theta. So 2 sine theta cos theta is sine 2 theta. Therefore, r dash can be written as u square sine 2 theta over g, and this is the value of the range. Therefore, r dash and r are numerically the same. So if we change the angle, we find the range does not change for that angle. So in these three figures, we are finding that the angle of projection in the first figure is 30 degrees, then 60 degrees. For 30 degrees projection, the trajectory is low, and for 60-degree projection, the trajectory is high. But the horizontal distance remains the same. That is, whether angle is 30 or angle is 60, the horizontal range will not change. The horizontal range is indicated on the horizontal line, OX line. Now in the second figure, the angle of projection is 45 minus alpha and other angle of projection is 45 plus alpha. So only the height of the trajectories are changing, but the horizontal range remains the same. Similarly, in the third figure, we find that angle of projection is 45 degrees, and for this projection, the velocity is indicated by u and the range is maximum. So, whatsoever the angle may be, the height trajectories, that is, the height of the trajectories can change, but the range will remain the same. So, horizontal range in all the three cases remains the same. So projectile has same range for the angles of projection theta and 90 minus theta, but has different time of flight, maximum height and trajectories. Range is also same for theta 1 45 minus alpha and theta 2 45 plus alpha. That is u square cos 2 alpha by g.